In this video, I'm going to demonstrate how to solve a certain kind of optimization word problem. These word problems are posted as a handout and also available in the slideshow. Let me start with this one, the lamp problem. A manufacturer has been selling lamps for $30 each, and they sell about 3,000 lamps per month at this price. The company would like to increase the price. After doing some marketing research, a manager determines that for each $1 increase in the price, they will sell about 200 fewer lamps per month. Suppose it costs the manufacturer $18 in materials and labor to make each lamp. How many lamps should this manufacturer make and sell each month to maximize profit? At what price should lamps be sold to maximize profit? And what is that maximum profit? So in short, this is about tuning a business to the point that the profit is maximized. The calculus part of this problem is really not all that difficult, but there's some significant algebra that you have to deal with before you can get to the calculus part. The solution that I'm going to show in this video is the one that you'll see in the homework tutorials that come with our software. This is not exactly my favorite way to solve these, but since many students see those tutorials and ask about it, I'm going to show you this solution here. So first, if you notice, there are no formulas in the problem at all. There are several numbers, but no formulas. That's the first challenge, that you have to go through the verbal description and figure out what the business functions are. Let's begin by kind of getting a handle on what the relationship is between price and numbers sold. So I'm going to begin just by making a little table here, and I'm leaving room for an extra column over here. I'll explain in a minute what goes there. So first, I'm going to put in the information about what the business is doing to start with. So they sell lamps for $30. That's a price. And under those conditions, they sell about 3,000 lamps per month. The per month business is just the time frame that this particular problem is expressed in. The company would like to increase the price. After doing some marketing research, a manager determines that for each $1 increase in the price, they will sell about 200 fewer lamps per month. Okay, this statement describes how the numbers sold and the price are related. In particular, if we add $1 to the price, which means we would consider selling lamps for $31, we'll sell about 200 fewer per month, which means that we would sell only 2,800 lamps per month. Now we could do all of this again. We could increase the price to $32, and that would lead to 2,600 being sold per month. So let me kind of gray out some of these lines. So the part that you see in green is the actual pairs of numbers sold and the corresponding price. What we'd like to do is build a function that expresses this relationship. The particular method of solution here is to do the following. I'm going to use the symbol x to be the number of steps down the table. That is, the number of times that we increase the price by $1 and decrease the number sold by 200. In this row, we have made 0 changes to the business. In this row, we have made 1 change to the business, And in this row, we have made 2 changes to the business. Now, I'm going to give these numbers sold and price single letter names. I'm going to let Q be the numbers sold, Q as in quantity, and I'm going to let P be the price. And that's a little p, you can tell because of the way I write it. Just so you know, normally we set up these business problems where X is the number sold, but for this solution method, for whatever reason, the material in our book and homework tutorial software uses X for the number of steps. Now I'm going to copy this information slightly more compactly here. In fact, let me just go ahead and call these Q, P, and X. So 3,000 at $30, no changes to the business. Sell 2,800 at $31, that's 1 change to the business. And 2,600 at $32, that's 2 changes to the business. We need to express Q and P in terms of X. Express Q and P in terms of X. Take a moment and try to do that. Let me start with P. P is pretty simple to look at and see. 30 goes with x equals 0, 31 goes with x equals 1, 32 goes with x equals 2. It should be clear that to get from x to P, just start with 30 and add x. So 30 plus x. And just to check, if x is 0, 30 plus 0 is 30. If x is 1, 30 plus 1 is 31. If x is 2, 30 plus x is 32. Okay, so far so good. It may be a little more difficult to do Q. Take a moment and try to write out an equation for Q as a function of x. Okay, here it might be a good idea to think of it this way. The number sold Q is the original 3,000, but then we have to subtract something. We subtract 200 for each step down the table. Well, 200 times x will do what we want, right? X is the number of steps down the table, so 200 times x is 200 for each step down the table, and then we need to subtract that. So just to make it clear what we're looking at, little p is the price at which lamps are sold. Q is the number of lamps sold. What's potentially confusing about this setup is that there is actually no demand function. So there's no demand function in this setup. Remember, the demand function gives price as a function of numbers sold. And we're expressing everything in terms of the number of steps down the table rather than in terms of numbers sold. So that means that when I go to write a revenue function, It's tempting to immediately write x times d of x, but that's not going to work because x doesn't mean what it usually means in this setup, and there is no demand function. So we're not going to do that. Instead, remember that conceptually, revenue is the total money collected from sales. If we sell some number of units at some price, do you remember how to build the revenue function from that information? Okay, remember, revenue is number of units sold times the price of a unit. In this setup, the number of units sold is Q, and the price of a unit is little p. So the revenue function that we're going to work with is little q times little p. We built formulas for p and q in terms of x. That's over here. So let me replace q, 3000 minus 200x times, and then p is 30 plus x. Now I hope you're thinking, what mistake am I about to make? What mistake are we always about to make? We need parentheses. You need to multiply the entire replacement for q times the entire replacement for p. If you don't have those parentheses, you're going to get a mess. Now that we've got this formula to start with, take a moment and simplify this, expand it out, and get r as a function of x. Okay, let's FOIL this out. First is 9 times 10 times 1,000 plus 3,000x minus inner is, well, 2 times 3 is 6 times 10 for the 30 times 100 for the 200 times x, then minus 200 times x is 200x squared. Now take a moment to combine like terms. Okay. These two are the only terms that combine. So we'll get 90,000 minus 3,000x minus 200x squared, and that's the revenue function. Now we need to build a cost function. Let's go back to the problem statement. Remember that there's a difference between cost and price. The $30 is a price. The $1 increase in the price is also a price. Those prices are always about what the business charges to its customers, what the customer pays to the business. For cost, that's always expenses the business must pay. And the dollar figure related to costs is in this statement. Suppose it costs the manufacturer $18 in materials and labor to make each lamp. So that's what we need to focus on when building the cost function. Okay, well, big C equals, well, we're only given information about per unit costs. So it's $18 per lamp in manufacturing costs. That means that we need to multiply the $18 cost by which symbol? We need to multiply by Q. That's the number of lamps that will need to be produced to meet this month's order. As before, I want to replace Q with its function, with its expression as a function of x. So that's 3,000 minus 200x. And that comes from up here. Now that we've got that far, let me just leave a note to myself here, replace Q. Again, you need parentheses because we want to multiply 18 times the entire replacement for Q. And without those parentheses, we'd have a mess. Now let's do some algebra to simplify this. We'll distribute the 18 times the 3,000 and minus 200x. The first part, 18 times 3,000 is 54,000 minus, and the second part is 3,600 times x. Now just to make this a little bit easier to see, I'm going to continue on the next page. So far, we have discovered that the revenue can be expressed as 90,000 minus 3,000x minus 200x squared. And the cost can be expressed as 54,000 minus 3,600x. Reading the problem statement again, our goal is to maximize profit and to find out what the business is like when profit is maximized. So we need a profit function. And do you remember the definition of profit? It's revenue minus cost. So P equals big R minus big C. If you notice, I'm writing my big P a little differently from my little p. That's to distinguish profit from price. Again, I'm going to fill in, so 90,000 minus 3,000x minus 200x squared to replace R. I'm going to put that in parentheses just to be safe. And then for cost, 54,000 minus 3,600x. The parentheses here and there are optional, but if it helps, by all means put them in. The parentheses around the cost function are definitely necessary because subtraction is asymmetric that way. Let's again expand everything out and combine like terms. These terms, the 90,000, the minus 3,000x, and the minus 200x squared that appear before the subtraction, we can just write out without parentheses. But then we need to distribute the subtraction over the cost formula that we've put in here. So we need minus 54,000 plus 3,600x. Now let's combine like terms. There are two degree zero terms. 90,000 minus 54,000, that leaves 36,000. There are two degree 1 terms, minus 3,000x plus 3,600. We'll add those together to get plus 600x. And there's one degree 2 term, so I'll finish by writing that minus 200x squared. At this point, it should be clear what we need to do next. What should we do next? Now we can get on with finding maximum profit. Well, how do you find the maximum of a function? Well, to maximize p, we need to look for critical points. Okay, how do you find critical points? We need to set the derivative, which I'll write in Leibniz notation for now, dp dx equal to 0, and solve. Okay, so dp over dx, take a moment to do that. Okay, you should get 600 minus 400x. And as I mentioned, the calculus part of this problem is really not that difficult. That's what we just did, and you could have done that much back in chapter 2. But now we'll set it equal to 0. 600 minus 400x equals 0, and we'll solve this. We'll subtract 600 from both sides. That leaves negative 400x equals negative 600. Then divide by negative 400. That leaves us with x equals negative 600 over negative 400. Be careful not to lose a minus sign while you're doing that. We'll get a double negative simplification, and if you like, you can simplify this all the way down to 3 over 2, which you can express in decimal form as 1.5. Okay, so we found x equals 1.5. What's a little frustrating about this is that 1.5 is not actually the answer to any of the questions we're asked. We aren't going to be making 1.5 lamps each month. The lamps are not going to be sold at $1.50, and the maximum profit is not $1.50. Instead, that 1.5 tells us how to configure the business to maximize profit. That means that what we need to do to answer all of these questions is figure out which function we need to evaluate and plug in that x equals 1.5. So for example, how many lamps should this manufacturer make and sell each month to maximize profit? That means that we should plug that x equals 1.5 into which function, evaluate which dependent variable. Yeah, how many lamps is Q? So the answer to part A comes from Q. So here goes. For part A, plug x equals 1.5 into Q. So Q, where x equals 1.5, is, well, we'll do 3,000 minus 200 times 1.5. And after some arithmetic, that evaluates to 2,700. So they should sell 2,700 to maximize profit. And that 2,700 is a reasonable number. If you look back at this table, if I squeeze in a row for x equal to 1.5, well, when x is 1, Q is 2,800. When x is 2, it's 2,600. So it makes sense that there should be a 2,700 squeezed in right there. Of Question B asks, at what price should lamps be sold to maximize profit? So what symbol should we evaluate? We're going to plug x into what function? We'll plug it into the price function, little p. So b, oops, change that. Plug x equals 1.5 into p. Okay, so p, where x equals 1.5 is, well, let's look up p. Again, that's over here. 30 plus x. So that's 30 plus x is 1.5. And that's easy enough. You can do that in your head, I bet. 31.5. So the price should be $31.50. By the way, that is also reasonable because, again, if you go back to this table and imagine squeezing in a row where x is 1.5, well, for x equal to 1, the price is 31. For x equal to 2, the price is 32. So 31.5 would squeeze right in there. So now we've answered questions A and B. Question C asks, what is that maximum profit? Well, if we used the quantity function to answer how many lamps, and we used a price function to answer at what price, it should be clear that to answer what is the maximum profit, we need to use the profit function. So let me insert another page. So plug x equals 1.5 into big P. So big P, where x equals 1.5, is 36,000 plus 600x minus 200x squared. And when you do the arithmetic, you get $36,450. Okay, so the maximum profit is $36,450. Now, you may be wondering, what if we wanted to be sure that we'd actually found a maximum? The trouble with what we have so far is that we have found a critical point. We've definitely found a critical number. But it might be a minimum, and that would be kind of silly to try to minimize profit. Turns out that there is a nice way to tell. For starters, this function profit, this is a quadratic function, so its graph is a parabola. Do you remember how to tell whether a parabola opens upward or opens downward? You find the quadratic term and look at its coefficient. If the coefficient, that's called the leading coefficient, if that is negative, the parabola opens downward. If it's positive, the parabola opens upward. This opens downward. Leading coefficient is negative, so graph opens downward. That means that whatever x is, the graph of p of x looks something like this. Let me put this on the axis. And right here is the critical point. And since the parabola opens downward, that critical point must be a local maxima. Furthermore, since this is a parabola, it's either a hill or a valley. There's no other zigzagging it can do. If it's a hill, then that local maximum is also an absolute or global maximum. So that confirms that this critical number that we found, this is indeed the value of x that maximizes profit. Another way to tell that's basically the same information is to remember that we have a second derivative test. dp dx we found to be 600 minus 400x. If I take the derivative again, I'll get d squared p over dx squared, which is negative 400. That's less than 0. That means that the graph of p is concave down everywhere. So again, we've confirmed that the critical point is the global maximum of profit because the graph is concave down everywhere else. There can only be a hill with its top at that critical point. And so the y-coordinate of that critical point, or I guess you'd call it the big P coordinate, is the actual maximum profit. So that is the parametric technique, as I've taken to calling it, for solving this kind of business problem. At the end, I do suggest that you go back and read the problem again just to be sure that you've answered all the questions. In the electronic homework, this isn't such an issue because there will be blanks for everything that you're supposed to put in. But on a test, sometimes students will forget to answer question B or question C, something like that. Also, it should be obvious that there's a lot that can go into a problem like this. I've written large and I've written a lot of extra information because this is a teaching video. But when you're doing these problems on your test, be sure to write neatly, write top to bottom and left to right, and be sure to label things. I will be looking through these for things to give you points for. Make it easy for me to find things to give you points for.